Hi, my name is John Krochmally, and I've created these video modules for people needing to understand and apply their skills knowledge to install, service, and maintain technology controlled by automation systems, and particularly the Programmable Logic Controller. Programmable Logic Controllers, or PLCs, are frequently found in many applications involving automation and instrumentation. In this presentation, we'll cover the typical wiring associated with the common Programmable Logic Controller analog output terminals. We will also explore the various troubleshooting techniques necessary to determine and correct problems related to PLC assembly analog output applications. There will be 4 learning outcomes to this presentation. Number 1, identify PLC analog output terminals. Number 2, provide power wiring to PLC analog output devices. Number 3, measure power supplied to the PLC analog output devices. And number 4, troubleshoot common PLC analog output problems. Where digital logic involves technology having only 2 states of condition, analog logic involves technology that provides or receives a value. Temperature sensors, damper actuators, and variable frequency drive motors all use values for their operation and are considered analog logic technology. Programmable Logic Controllers, or PLCs, come in a vast array of sizes and designs. The Allen Bradley Compact Logics, Micrologics, Control Logics, SLC500, and the Omron Mini PLC are usually rack-mounted and come in various combinations consisting of input and output modules. The rack mounting usually involves DIN rails that these units can be easily placed into or taken out of. The Compact Logics, Control Logics, and SLC500 assemblies will have their analog output modules assigned in specific locations in their assembly array as shown. Micrologics and Omron Mini PLCs are considered to be brick controllers, and because of their design may not have analog functions. In this presentation, we'll use this graphic for orientation purposes, as well as to understand analog output wiring concepts. As we may remember, digital logic involves 2 and only 2 conditions. Something is either on or off. Analog logic involves actual values. Something is closed, a percentage open, or fully open. In the case of this example, the mixed air damper actuator can be adjusted to be fully closed, 35% open, 75% open, or 100% open. These represent analog logic examples. The graphic shown is a typical layout of the electrical circuit utilized by PLCs for the output control of analog devices. Notice that a separate power supply powers the entire PLC analog outputs. This same power supply supplied working power to the mixed air damper actuator and the PLC analog output module for the PLC assembly. The manipulation of the output device, in this example a damper actuator, starts in the PLC processor. In this example, 20 volts DC is sent to the PLC analog output module to change the value of the electronic signal controlling the analog output load. Because PLC analog output devices are operating on direct current and voltage, it is very important to make sure that all wiring observes the electrical polarity of devices. If devices are wired against this polarity, they will not work as designed. Our understanding of the troubleshooting procedures involving PLC output sections can start with this graphic showing electrical circuit intentions. In this graphic, we see the supplied power feeding both the output analog load as well as the PLC analog output section for its control. For installation of analog output devices to the PLC assembly, we can start with bringing and measuring for power to the power supply feeding the outputs. Notice the placement of the voltmeter to measure the source voltage. Using a solar power supply, we can perform this measurement on terminals for power input. In this example, between L1, line voltage, and N, neutral. The next step in installation measuring involves the voltage measurement at the power supply output. Remember that the power supply converts voltage AC to voltage DC, and that the power supply output voltages could be 24 volts DC, 12 volts DC, or another voltage DC. If the power supply is working properly, the measured voltage on the output would be the same as the labeled output voltage on the power supply. In this example, 24 volts DC. Since the PLC analog output module needs to have power in which to operate, we can measure this power at the PLC analog output module. When measuring voltage DC, remember to observe lead polarity when using voltmeters for voltage DC measurements. In our installation and troubleshooting process, we can also bring to and test power at the analog load device. In this example, the power to the mixed air damper actuator is measured in voltage DC. This graphic represents a ladder diagram showing the circuit logic among the power supply, analog output module, and its controlled loads. Our first step in troubleshooting would be to measure the voltage coming into the power supply. In this case, we expect 120 volts of AC power. Our next step would be to check the power coming out of the power supply. If the power supply is operating correctly, the listed output voltage of the power supply will be measured. Since the power supply feeds the reduced voltage DC to the output module, we should read that step-down voltage DC at the module's common terminal. One more step to be taken when verifying voltages DC involves voltage actually registered on the PLC output module terminals. Voltages appearing here should be the same values as the output voltages of the power supply. The previous steps involve DC voltage measurements, involve the circuit power being applied. The variation of control signals is what is performed by the PLC's analog output section. These control signals may be in voltage DC or in amperage. Most industrial control signals will be in milliamps and usually in the 4 to 20 milliamp range. Using this example, the actual value of the control signal to the load under control can be measured. Shown in this graphic is the placement of a milliamp configured multimeter between the A0-0 PLC output terminal and the analog load. The amperage configured multimeter scaled to read in milliamps can then measure, in this case, between 4 to 20 milliamps. It is important to understand that when performing milliamp measurements on DC electronic equipment, the meter is placed in series between the source of the current and the receiving device. Also, it is also important to observe circuit polarity. Referencing this graphic, we see a mixed air damper actuator whose blades swing in a 90-degree arc from fully closed to fully open. With the analog output signal, blade positions can be commanded to a specific position between 0 and 90 degrees. the value of the milliamp signal sent to the control terminals of the mixed air damper actuator will achieve this intended position. Here is a picture of a graph associated with the mixed air damper position control. Utilizing a 4 to 20 milliamp control signal, we can open or close the damper. We can also achieve a precise position of the damper condition. In this example, if 4 milliamps are sent to the actuator control terminals, the damper will be held in a closed position. If we increase the control signal to the actuator control terminals to 20 milliamps, the damper will be driven to a fully open position. If we want the damper to be open 50%, we can send a signal of 12 milliamps to achieve this position. We can use our milliamp configured multimeter to measure the PLC output module's control signal to the analog device by placing this meter in the position as shown. Remember when performing measurements to observe circuit polarity.